Welcome to this first video on capacitors. In this video, we're going to look at what capacitors actually are, how they work, and some of the formulas we're going to need to know for them. So to start off, a capacitor is two plates that hold charge on them. So two plates right next to each other. In this case, a top plate and a bottom plate. Now that's going to be connected up to some kind of circuit with a battery, in this case a 12-volt battery. And what will happen is you've got the positive terminal of the battery and the negative terminal of the battery. You've got all these charges, positive and negative, in the wires. And what's going to happen with the battery voltage, this 12 volts, is it's going to push the positive charges around onto this plate and the negative charges around onto the bottom plate here. So because of this big pushing force, we're going to start to get some positive charges building up on the top plate and the negative charges building up on the bottom plate as the battery pushes the charges onto those plates. But what then happens is you have all of these positive charges sitting next to each other. They don't like it. Positive and positive repel each other. Same with all these negative ones sitting next to each other. They don't really like it. They want to repel each other. So you start to get on these plates some kind of repulsive force, which is an opposing voltage. We call this epsilon. This is the capacitor voltage. So this repulsive force of these charges pushing back against the battery creates its own voltage. Now to start with, when we only have a few charges on here, that repulsive voltage, little epsilon here, capacitor voltage, is quite small. But as the battery keeps pushing more charge on there and the charge builds up, the capacitor voltage gets a little bit bigger. And then as you put even more charge on it, it gets really big until finally the repulsive voltage, or the capacitor voltage, is pushing backwards against the battery with the same force. So the battery is trying to push charges around here with 12 volts of energy, whereas the capacitor is trying to push back with its repulsive force, again with 12 volts of energy, and that is when the capacitor is all charged up. So the positive forces repelling each other and the negative forces repelling each other push back against the battery eventually so hard that these forces all balance out, or these voltages. So the capacitor voltage will equal the battery voltage. So that's how a capacitor works. It gets charged up by a battery, and then these plates hold charge. That's why a capacitor is two plates that hold charge. So now let's look at how we measure that. The ability to hold charge is called capacitance. That's how we measure how good a capacitor actually is. So we have this formula here for capacitance. It's got all these four different things. So C here is capacitance, and we measure this in farads. It's just the unit we use to measure how good a capacitor is at holding charge. We have this little symbol here, E naught or epsilon naught. And this is called the permittivity of free space. It's just a constant. It's a number to make sure the whole formula balances. This will never change, and you're given it in your exams. All you're going to need to remember is that this symbol, epsilon naught, in your equation is called the permittivity of free space. And they'll tell you this 8.85 times 10 to the minus 12 in your exam. It's just a number. Then we've got this little ER here. Looks really similar, but this is what we call a dielectric constant. Then we have A, the area of plates, and D, the distance between plates. We're going to go through these last three one by one, because these are the three things that affect how good a capacitor actually is. So to start off with distance between the plates, you can imagine that these positive charges and these negative charges are trying to get off the plates. They have their opposing voltage because they're repelling each other. But if we move the plates closer together, then all of a sudden we can fit more charge on because of the attractive force between the positive charges on the top plate and the negative charges on the bottom plate. The positive charges are happier sitting up here because they're closer now to a negative charge, so they're not repelling each other quite as much. Same with the negative charges. They're happier sitting on this bottom plate because they're closer to a positive charge. So all in all, because the charges are closer to each other and the charges are a little bit happier to sit there, we can fit slightly more charges on this plate. Therefore, we have a greater capacitance if we can get them closer together. Now, the second thing that affects it is the area of overlap of the plates. So if we created plates which were twice as big, then we have twice as much space to store charges on. So therefore, we can store more charge on these plates. They just have more places to spread out and go before they're repelling against each other quite so hard. So that's why the area has a direct impact on how good the capacitance is. Now you'll notice that it's called area of overlap, and that these two plates are overlapping directly. If we happen to extend one of the plates out that wasn't overlapping, no charges would go on there, or no charges that we care about. And that's because these positive charges love sitting next to the negative charges on that opposite plate, and vice versa. Therefore, they're not going to go way out on this kind of extra area because they can't get close to their negative charges. So the only area that counts is the areas that are overlapping with each other. So that's why it's called the area of overlap. Now finally, we can learn about this thing called a dielectric constant. So if we go back to our original capacitor, you could jam something in the middle of these two plates, which is an insulating layer. Now, it has to be insulating because if it could conduct, if the positive could go to the negative, you'd just really have a big fat section of wire here, so it wouldn't be a capacitor anymore, wouldn't store the charge. Inside this insulating layer, you're going to have a whole lot of atoms. Now, atoms have negative electrons around the outside and a positive nucleus. And what happens, because we've got a very positively charged top plate and a very negatively charged bottom plate, the atoms are going to become polarized, they'll get stretched. So the nucleus that's positive will get pulled down towards the bottom, sitting close to the negative plate. Whereas the negative electrons will get pulled up to the top to sit close to the positive plate. So you're getting a negative end to this dielectric, which gets negatively charged, and a positive end to the dielectric, or side to the dielectric, because of the positive nucleus is getting pulled downwards. Now this is great because the positive charges on the top are even happier sitting on this plate, knowing that there's a negative charge right next to them. And the negative charges on the bottom plate are really happy knowing that there's a positive charge very close to them. It's all because negatives are attracted to positives and positives to negatives. So it means we can fit a bunch more charges on both of these plates, which again increases this capacitance. So these are the three things which can impact capacitance. You'll get told numbers for all of these things and you can plug them into your formula if you need them. Now, if you ever had to do a calculation, you know that E naught is always this 8.85 times 10 to the minus 12. You get told a dielectric constant, and this will be a number. If it's air, it's just 1, which means it's just like having no dielectric timesing something by 1, which it doesn't because it's air. So if you had a dielectric constant of 2, it would mean that whatever you chuck between the plates means that the plates can store twice as much charge as they could before. Or a dielectric constant of 4 would mean they can store 4 times as much charge as they could before. So you get told that number. You get told the area of overlap of the plates and the distance between the plates, sometimes called the plate separation as well, distance between the plates. So that's what impacts capacitance here. But we've also been talking a lot with charge. So let's look at a formula for charge. Charge is called Q, and this is given by the capacitance and the voltage. So think you're going to have more charge if you have a greater capacitance. Capacitance is just the ability to hold charge. So if you can hold more charge, you will. And if you have a stronger battery pushing the charges on with greater force, you're also going to have more charges stored on these plates. So the charge is given by the capacitance multiplied by the voltage. So charge is measured in coulombs, which is C. Capacitance, again, we've mentioned, is measured in farads, which is capital F. And voltage is the same, measured in volts. So you might get some kind of question like this. When a capacitor in the circuit is fully charged, it holds 1.7 times 10 to the minus 4 coulombs of charge. And we need to calculate its capacitance. So going to our classic charge formula, Q equals CV, if we want to calculate the capacitance, we're going to have to rearrange this. So rearranging for capacitance C, it equals the charge divided by the voltage. So we can put in the charge that we know is 1.75 times 10 to the minus 4. We can put in the voltage, which we know is 12 volts. And remember, the capacitor is going to be repelling with 12 volts once it's fully charged. That's how we know it's 12 volts. Putting that into your calculator is going to give you a capacitance of 1.46 times 10 to the minus 5 farads. So we've got our capacitance. Now the final formula or thing we need to understand is energy. There's a whole lot of energy stored on these plates. It's because of the electric field. And the electric field is really the repulsion force between all the positive charges and all the negative charges trying to escape from each other. That's got potential energy in it. So energy is still measured in joules like always. We've got our charge and we've got our voltage. So we could use this formula in a question like this, where when fully charged, we hold the same amount of charge, 1.75 times 10 to the minus 4. We need to calculate the energy stored in the capacitor. So we whip out our formula. It's half times charge times voltage. We put in our charge of the 1.75 times 10 to the minus 4. We put in our voltage of 12. And then plug in all of that into your calculator. You're going to get an energy of 1.05 times 10 to the minus 3 joules. So this is how you calculate energy that's stored in a capacitor. Finally, we've been looking at a 3D model for capacitors, but in your circuits, this is just drawn as two plates or two lines right next to each other. This is what a capacitor looks like. It's really similar to what a battery looks like, except a battery has one long side and one short side, whereas a capacitor has two sides that are exactly the same length. And we don't want to have to draw this in 3D, just like we don't want to have to draw a proper picture of a battery. We just want to draw the symbol for a capacitor. So this is what you'll see in your exams. So now let's look at what you need to know. We learned that capacitance, C, is the ability for two plates to hold charge, and charge is Q. And we learned that that's given by our capacitance formula, where we have E naught, that's the constant we're always given, permittivity of free space. We also learned about the distance between plates, D here, and that if plates are closer together, they're going to store more charge, so we're going to have a greater capacitance. We then learned about the area of the plates. If you have more area, you give more space to hold the charges on, so that also increases capacitance, and that's given in this formula. And we learned about ER, the dielectric constant. And a dielectric is just an insulating layer which sits between the plates. And this works because you polarize the atoms inside this layer, so it gives a negative side and a positive side. And you'll get a number for this insulation layer, this dielectric, called the dielectric constant. And you plug that number in for R. It'll usually be somewhere between 1 and 5. We also learnt about the charge formula, charge equals capacitance times voltage, and the energy formula. Energy is a half times charge times voltage. Finally, we learned that a capacitor is just two plates sitting next to each other, and this is the symbol here, two lines of equal length sitting next to each other in your diagram. So let's look at some questions now of how we do this. Here we've got a circuit, and in this circuit we've got switch B, which is kept open, and switch A, which is going to be closed, and that means charge can flow onto these capacitor plates. This is our capacitor right here in the middle. So we're going to need to explain why the voltage of the capacitor rises up to equal the voltage of the battery. So now to start with, we can say switch A gets closed, therefore we can ignore the whole bottom part of the circuit just to make this a little bit more simple. And then we can answer our question. So the first thing you want to kind of say is, initially you've got a big battery voltage, much higher than the capacitor voltage. So the capacitor, before we've even started, is nothing. It doesn't have a repulsive force until the battery starts pushing charge around onto it. Then the charge starts to repel, so it creates a repulsive force or an opposing voltage. That's the capacitor voltage. So we could write that initially the voltage of the battery is higher than the voltage on the capacitor. So charge is going to be overall pushed onto the capacitor. And then you can say that over time, as the charge increases, the voltage, that's the repulsive force, on the capacitor will increase. It's shown by this formula. If we have the same capacitance that's set for a capacitor, but we have a small amount of charge on there, we're going to have a small amount of voltage. But as we put more charge, Q, on there, we're going to get more voltage building up on the capacitor. Finally, when it's fully charged, the pushing voltage of the battery equals the repulsive voltage of the capacitor. And therefore, we're going to get no charge flowing. It's fully balanced because the voltage pushing it is going to be equal to the repulsive voltage pushing backwards in the opposite direction. Now, while you have a full answer here, you can actually use a different type of explanation from our DC circuits, our last video, using Kirchhoff's voltage law. Now, that says that the voltage around a closed loop equals 0, and you could say that the resistor has no voltage because there's no current flowing through the circuit anymore when they're balancing each other out. Therefore, because of Kirchhoff's voltage law, you have 12 volts from the battery is going to be balanced out by the opposite 12 volts or negative 12 volts from the capacitor. There's no voltage across this resistor here. So you could also use Kirchhoff's voltage law to explain this, and they do in some answers, but a full explanation of what actually goes on is good too, and that's a merit level explanation. Now let's look at another question. We've got the capacitor fully charged with a charge of 8.6 times 10 to the minus 3 coulombs. And we need to calculate the energy stored in the capacitor, which is great. We know our energy formula, half times Q times V. We know that we have a Q of 8.6 times 10 to the minus 3. We know that we have a voltage of 12 volts. Therefore, we can plug our numbers into our formula. Half of Q multiplied by the 12 volts gives us a final energy of 0.052 joules. It's an achieved level question. It's what we call a plug and chug. We find our formula, plug our numbers in, and chug out the answer. All right, then we do C. Here we've got a new circuit. We have a 9-volt battery here, which is being used to charge this capacitor on the other side. So at one point during the charging, the capacitor has a voltage of 6.4 volts, and the current flowing in the circuit is 0.208 amps. So we need to show that the internal resistance here, R, of the cell is 12.5 ohms. So the thing you need to understand is you've got two voltages at play here. You've got the voltage of the battery, which is pushing hard around clockwise, or in this top branch, it's going left to right. But you've also got the opposing voltage of the capacitor, which is pushing backwards against that at 6.4 volts while it's charging. These voltages going in opposite directions cancel each other out, which leaves an overall voltage of 2.6 volts. So now that we have this voltage, and we know the current in the circuit is 0.208 amps, we can find the resistance in the circuit because this resistor is the only resistor in the whole circuit. So using our V equals IR formula and rearranging that for R, we get voltage divided by current, which is the voltage of 2.6, the overall voltage, divided by the current we know, 0.208, gives us a final resistance of 12.5 ohms, which is what we wanted. And this is a merit level question. Then we could look at the same circuit. It says the capacitor has air between its plates, and a plate separation, that's a distance between the plates, so 2.26 times 10 to the minus 4 meters. So if this capacitor has a capacitance of 2.75 times 10 to the minus 9, what's the overlap area of the plates? So this is going to involve our original equation. So taking a close-up look at the capacitor, we know that we have a distance, we've got air in the middle of it, and if we look at the plate in 3D, we're going to have an area on those plates. So we can write down everything we know. We know that we have a capacitance of 2.75 times 10 to the minus 9. We know that we have a permittivity of free space, that's epsilon naught, of 8.85 times 10 to the minus 12. We have a dielectric constant of 1 that we get told. We're always going to get told this. And we have a distance between the plates, the plate separation, of 2.26 times 10 to the minus 4. So knowing all of this, we can use our first formula for capacitance. We need to rearrange this so to find area, because we're trying to find the overlap area of the plates. So in that case, we multiply both sides by D, divide both sides by epsilon naught epsilon r, and that gives us the formula for A, for the area. Plugging our numbers in, we've got capacitance multiplied by the distance between plates, all divided by this permittivity of free space multiplied by our dielectric constant of 1. Putting that into your calculator gives you an area of overlap of 7.02 times 10 to the minus 2 meters squared. So this is how we use capacitors. We covered what capacitors are, the two plates, how they work and all the things that alter them in terms of area, distance between plates and the dielectric in the middle of them, and we learned about charge and energy of these plates. So this is capacitors.